In this module, we will discuss state space modeling. Specifically, we'll introduce what we mean by state space form, and we will discuss how it relates to the other modeling formalisms we've used so far in this course, specifically regular differential equations and transfer functions. We'll then talk about how to put a system into state space form, and we will discuss how to transfer between model types, specifically between state space form and transfer function form. Finally, we'll go through an example. A state space model represents a system as a series of first-order differential state equations and algebraic output equations. So that being said, state space form is basically just differential equation form, but the differential equations have been rearranged as a series of first-order differential equations. That is, the highest order of the derivative is just a first derivative. The reason that we use state space models is because they can be numerically efficient to solve, they can handle complex systems, they allow for a more geometric understanding of dynamic systems, and they form the basis of much of modern control theory. So some of this won't be entirely clear. I will try to point some of it out through the course of this module. Some of the benefits and disadvantages won't be seen until later when you actually get into designing controllers and estimators in this using these types of models, using state feedback control, designing observers, and then much of sort of optimal control theory uses state space models, linear quadratic control, Kalman filters, etc. So here is a model of a physical system, a dynamic system. And if we look at it, we have a third-order differential equation modeling the system. By definition, this is not in state space form. In order to be in state space form, we need to model the system as a series of first-order differential equations. Here, the highest derivative is third order. Therefore, one way to put a differential equation model into transfer function form is to simply do a change of variables. So here we have a third-order differential equation. By choosing this new set of variables, we can rearrange this as three first-order differential equations. So we have a variable for the lowest derivative, the zeroth derivative, the first, and the second. The highest derivative does not need its own state variable. So here we repeat the original differential equation. We're going to do this change of variables in order to put it into state space form. For each of the state variables, we're going to have a single differential equation. So our first state variable, x1, we're going to have a differential equation for it. x2 will have its own differential equation, and x3 will also have its own differential equation. Examining this, x1 is equal to x. Therefore, its first derivative is x dot. In terms of the state variables that we've defined, x dot also happens to be equal to x2. Okay, so there's our first differential equation. Similarly, x2 dot, since x2 is equal to x dot, x2 dot will simply be x double dot, which happens to be equal to x3. And then finally, x3, its first derivative is x triple dot. We don't have a state variable equal to x triple dot, but we do have the original differential equation, which we can express x triple dot in terms of the other state variables. So if I subtract all of these terms to the other side, I have negative 5x double dot, where x double dot is x3. I have negative 3x dot, where x dot is x2. And I have negative 2x, where x is x1. And then I already had a u on the other side. And so what we've done is we've taken our original third-order differential equation model and written it as three first-order differential equations. We define these three equations as our state equations. State space form also includes an output equation or a series of output equations. What defines the output is sort of an engineering decision. It depends what we're trying to control. It depends what we're trying to analyze. So position could be the output, velocity could be the output, both could be the outputs. So let's say arbitrarily that in this case, x dot is the output. That just means that our output is x2 because x dot is equal to x2. This is something that you'll have to be told or you'll have to decide based on what it is you're trying to accomplish. So looking at this is a complete state space model of the original differential equation. This particular system has one input, u, it has one output, y, and it has three state variables, being the x1, x2, and x3. In general, state space models have the following form. Okay, so we have a derivative for each of the state variables, and each of those derivatives is a function of the other state variables and all of the inputs, where there could be more than one input. You'll notice that these are all first-order differential equations. They have a single first-order derivative being a function of non-derivatives, of only state variables and inputs. One thing that's interesting to note is that these functions can be nonlinear and they can be time varying. So the function itself could be a state variable squared, it could be the sign of a state variable, etc. Furthermore, the coefficients don't necessarily need to be constant. They can change with time. So this is a very general format that's applicable to basically any sort of dynamic system. Similarly, we have output equations, which are algebraic equations. There are no derivatives in the output equations. In this case, we have p outputs, and each output is a function of the state variables and the inputs. So this is the most general form of a state space model, where it could be linear or nonlinear, varying or time varying. If it turns out that our system of equations are linear, then we can rewrite them as matrices. And this is the general form. So we have a vector of the derivatives of all of the state variables. We have a matrix A multiplying the vector of state variables. We have a matrix B multiplying the input variables. So this matrix equation constitutes all of the state equations. And then we have a second matrix equation for all of the output equations, where we have a vector of outputs equal to a C matrix times a vector of state variables plus a D matrix multiplying a vector of inputs. So if we consider our previous example, here are the state equations, here is the output equation. We can rewrite this in matrix form because these are linear equations. So specifically, we'll have a vector of derivatives of our state variables, x1 dot, x2 dot, and x3 dot. We'll have an A matrix multiplying a vector of state variables. We'll have a B matrix multiplying a vector of inputs. In this case, we have only a single input, a scalar input. And then we'll also have our output equations. We'll have a vector of outputs. In this case, we have only a single output, a scalar. We'll have a C matrix multiplying a vector of state variables. And we'll have a D matrix multiplying our input vector, which in this case has only one element. So looking at the first part with our A matrix, the first row of the A matrix is going to represent our first state equation. So x1 dot is equal to x2. So that means that the first row of our A matrix is going to be 1. It's going to be 0, 1, 0. If we took this row and multiplied it by that column, we would get 0 times x1 plus 1 times x2 plus 0 times x3, meaning x1 dot is equal to x2, just as we have here. Since the first equation is not a function of the input u, that row of the B matrix is just 0. The second row represents what x2 dot is equal to. So it's 0 times x1, 0 times x2, 1 times x3, and 0 times u. And then the last row constitutes the equation for x3 dot. So multiplying x1 is a negative 2, multiplying x2 is a negative 3, multiplying x3 is a negative 5, and multiplying u is 1. So there we've filled out our state equations. We have an A matrix and a B matrix. We do the same thing for our output, where y is equal to 0 times x1 plus 1 times x2 plus 0 times x3 and 0 times u. So there is our previous example put into matrix form.